Welcome again to this presentation. Today we are going to discuss again the questions and the answers regarding thermochemistry. Last time we ended on question 41. Today we are starting on question 42, and then we will also discuss question 43. Question 42 is asking by using equations, explain how the internal energy, heat, work done are calculated for isochoric process. Isochoric process is a process occurring at constant volume. Let's see the answer. An isochoric process is a process that takes place at constant volume. For an isochoric process, the volume should be constant. So that means the change in volume is 0 and the work done is also 0, because remember the work done is equal to negative PDV, and if the change in volume is equal to 0, that means automatically the work done is 0. If the work done is 0, remember the internal energy is equal to NCV dt, and the internal energy is equal to the heat time plus, if you have the internal energy is equal to the Q, which is the heat plus the work done. If the work done is 0, that means internal energy is equal to the heat. So here we have the internal energy is equal to the heat plus the work done, and if the work done is 0 here, that means the internal energy is equal to the heat. The heat is equal to the internal energy and is equal to NCV dt. Again, when you have the isochoric process, so we have what you call the Guy-Lussac law, where we have a constant volume at constant volume. When you have at constant volume, the pressure of the gas is directly proportional to the temperature. That means we can also use this formula, P1 over T1 is equal to P2 over T2. At constant volume, can calculate the final pressure or the final temperature by using P1 over T1 is equal to P2 over T2. That is according to Guy-Lussac. At constant volume, the pressure of the gas is directly proportional to the temperature. So far we have the internal energy, which is equal to NCV dt. We have also the heat, which is also equal to the internal energy is equal to NCV dt, and we have the work done, which is equal to 0 for isochoric process. Isochoric process can be either an expansion or a compression. So we have seen that the isochoric process, the work done is equal to 0. That means the internal energy is equal to the change in the heat is equal to the heat, and this isochoric process can be equal. It can be an expansion or a compression. When it is an expansion, that means you have the du is equal to NCV dt, the constant volume, and you have NCV du is equal to NCV dt. We have the dV is equal to 0 because we have the constant volume, and the work done is also equal to 0, and the heat is equal to NCV dt. And when you have a compression, also we have the dV, which is the change in volume is equal to 0, and the work done is equal to 0. Again, the internal energy is equal to NCV dt, and also here the heat is equal to NCV dt because the work done is equal to 0. Here, when you have isochoric process, it's a process occurring at constant volume, and the process occurring at constant volume, the dV is equal to 0, the change in volume is equal to 0, the work done is equal to 0, and the internal energy is equal to the change in heat. So internal energy is equal to dQ. The internal energy is equal to the heat for isochoric process. If you have again an isochoric process, we have the PV is equal to nRT. The pressure times the volume is equal to nRT. In this case, we can also have the change in pressure times the volume is equal to nR dt. So we are changing here the change in temperature. We are introducing the change in temperature here, and also we are introducing here the change in pressure times volume. That means the delta T, which is the change in temperature, will be equal to the change in PV dividing with nR. In this case, then we have the dq, which is the heat. The change in the heat is equal to NCV dt. Then we can change here the change in temperature by this component. In this case, then we have the dq is equal to NCV, the change in pressure times volume over NR. So can say that the dq, which is the heat, is equal to NCV, the change in pressure times volume over R. So you can also use, if you have the change in pressure times volume, you can also use this formula for calculating the change in the heat at the constant volume or in the isochoric process. Isochoric process can also be either reversible or irreversible. If you have the isochoric process and you have the reversible, you might be having a slow process because it is a reversible. In this case, external pressure is not constant because remember we have seen that in a reversible process, external pressure is not constant. In this case, we calculate the pressure of the gas is almost equal to the pressure, to the external pressure. In this case, we can calculate the work done by using the pressure of the gas. But in this case, the dV is equal to 0. If dV is equal to 0, that means immediately the work done, whether you have the reversible process here, the work done is 0 because the dV is equal to 0. If you are considering also the irreversible process, external pressure is a constant. In this case, we can use the external pressure, but by using external pressure to calculate the work done in reversible process, in this case also, the dV is equal to 0 because we are in isochoric process, the change in volume is equal to 0. In this case, we have also the work done, which is irreversible, is equal to 0. So whether in the isochoric process we don't differentiate reversible and irreversible, we know that the work done is equal to 0 because the change in volume is 0. So you have seen that for a diabatic process and for the isothermal process, we are differentiating the formula of calculating the reversible process and the irreversible process. When we are calculating the work done for reversible and the irreversible process, we are differentiating different formula to calculate the work done. But here in isochoric process, because we are having the constant volume, here the work done is 0. So we don't differentiate whether you are in a reversible process or whether it is irreversible process when you have isochoric process or where you have a process occurring at the constant volume. What you need to retain here is that you need to retain that for isochoric process, the work done is equal to 0 and the internal energy is equal to the heat, is equal to heat, and also internal energy is equal to NCV dt. That means the heat also is equal to NCV dt at the isochoric process or a process occurring at the constant volume. Let's move to question 43. Question 43 is asking, by using equation, explain how internal energy, heat, and work done are calculated for isobaric process. Isobaric process is a process occurring at constant pressure. In this case, the isobaric process is a process that takes place under constant pressure. For isobaric process, it is a process which is occurring at a constant pressure. The pressure is constant. That means the change in pressure is 0. dP is equal to 0. If the pressure is constant, we know that the du, which is the internal energy, equal to NCV dt. Internal energy for all the process is equal to NCV dt. Then we know that internal energy is equal to Q, which is the heat plus the work done. Then the heat is equal to NCP dt. Here we are not having the constant volume, we are having the constant pressure. That's the reason why for this heat we use the CP, the molar heat capacity at constant pressure. In this case, Q is equal to NCP dt. In this case also you can use the Charles law equation, which say at constant pressure, the volume occupied by a fixed amount of gas is directly proportional to the temperature. That means you can also use this process, you can use this equation where V1 over T1 is equal to V2 over T2 when you are having isobaric process, or when we are having a process occurring at constant pressure. This is the Charles law, the formula that we have seen when we started the gas law equations. So remember, we say the Charles law, at constant pressure, the volume is proportional, the volume of the gas is directly proportional to the temperature. In this case, we have V1 over T1 is equal to V2 T2. We can calculate then the final volume and the final temperature by using this equation. Again, when we are having the isobaric process, we can also have an expansion or a compression, expansion occurring at constant pressure, or a compression occurring at constant pressure. So when you have an expansion, the gas is expanding, the volume is increasing, the dP is equal to 0. Of course, the internal energy is equal to NCVDT. We have seen that in all the processes that internal energy is equal to NCVDT, and the dQ, which is the heat, is equal to NCPDT. And when you have the heat at constant pressure, in this case, it is also called the enthalpy. Enthalpy is the total heat, the content of the system at constant pressure. Then we have also the work done is equal to negative PdV, or is equal to nRDT. Here, when you have an expansion, remember the work done is negative, and the dQ is positive when you have at a constant pressure, because when you are expanding, that means the pressure is going to decrease, and by decreasing the pressure, for the pressure to stay constant, there should be a supply of the heat from external sources. In this case, then, the dQ is positive. The system gets the heat so that the pressure stays constant. Again, delta W, or the work done, is negative because the system is expanding. You might also having a system which is not expanding but it is compressed. The compression process is the same. If you have the isobaric process, delta P is equal to 0. The internal energy is equal to NCVDT, because we have constant pressure. The internal energy is equal to NCVDT. Remember, we have demonstrated that internal energy for all process, whether you have a constant pressure or you have constant volume, we have seen that internal energy is equal to NCVDT. In our previous courses, we have seen that the internal energy, whether you have the constant volume, whether you have the constant pressure, is equal to NCVDT. Again, the dQ, which is the heat, is equal to NCPDT. It is also called enthalpy. I told you that is called enthalpy. When you have the heat at constant pressure, it is called the enthalpy. We call it enthalpy. Is a specific term that we use when we are referring to a heat at a constant pressure. We are referring to it enthalpy. We are referring to it as enthalpy. In this case, the work done is equal to negative PdV is equal to nRDT. Then we have the work done, which is positive because system is compressed. We are compression. The work done is positive, and the delta Q, or the heat, is negative, because when you are compressing, the heat is going to increase, and then if the heat is going to increase, to get a constant pressure, in this case, a heat must be removed. There is a release of the heat so that the pressure can stay constant. Isobaric process can be also either reversible or irreversible. We have isobaric process which is reversible. In this case, the slow process, but here the pressure is constant because we have isobaric, we are at constant pressure. Then here also, when you have the irreversible process, the fast process, but the pressure is constant. Because we have isobaric, the pressure is constant. We use the pressure of the gas, which is constant. Here also we use the pressure of the gas because the pressure is constant. Again, here, when you have isobaric process, we don't differentiate whether we have reversible or reversible in calculating the work done in reversible and the work done in irreversible process. You can see that we have the same formula to calculate the work done in reversible and in irreversible process. When you are having isobaric process, remember, isobaric process is the process which is occurring at a constant pressure. The pressure is constant in irreversible process, the pressure is constant also in irreversible process when you have isobaric process. In this case, we can use the same formula to calculate the work done, which is reversible, and the work done, which is irreversible, and the work done is equal to negative the integral P dV. In this case, because the pressure is constant, we can put this P aside, the pressure aside, and then we integrate dV. The integration of dV is V. In this case, then we have the work done is equal to negative PV times V, but we need to integrate from V1 to V2. That is V2 minus V1. In this case, we have the work done, which is reversible, or the work done irreversible, when you have the constant pressure is equal to negative P V2 negative V1 minus V2 minus V1. In this case also, we can say that is equal to P V1 minus V2 when we are putting this negative inside the bracket. So this is the formula that will be using to calculate the work done when we are having the isobaric process, or a process occurring at constant pressure, whether you have reversible or whether you have irreversible. It is the same. We have the work done, which is equal to pressure times V1 minus V2. Again, when you have this kind of equation, you can we can have another structure of this equation. Remember, I told you that when you have the Q, the heat at constant pressure, we are referring to as enthalpy. In this case, let's say that we have the du internal energy is equal to the heat plus the work done. When you have the heat, which is enthalpy, the heat is equal to the internal energy minus the work done. So we have this heat is equal to internal energy minus work done. Then you can replace the work done by its value. The work done is equal to P V1 minus V2. In this case, we can have the heat is equal to, here the change in internal energy is equal to the final internal energy minus the initial internal energy. Then here the work done, you have replaced the work done by P V1 minus V2. This is the formula here. The work done is equal to P bracket V1 minus V2. That's where we have replaced P V1 minus V2 by dW. Again, here we have the Q, which is the heat, is equal to final internal energy minus initial internal energy. Negative, we are PV1 plus PV2. This negative times negative, we get here positive. Negative PV1 plus PV2. Then we have the heat, which is equal to the final. This is the final internal energy, then plus PV2. Negative, here negative, here the initial internal energy, plus PV1. So this PV1, if you are then multiplying, we are putting the negative aside. So we are putting the negative aside, then we remain with the initial internal energy plus PV1. Then, so what is this one? So remember, so this is what we call we have said that the heat is equal to the enthalpy. The heat is equal to enthalpy when you have the constant pressure. When you have the constant pressure, a process at constant pressure, the heat is equal to enthalpy. At the constant pressure, when you have isobaric process, the heat is equal to enthalpy. The enthalpy is equal to internal energy plus the product of pressure times the volume. That is enthalpy. That means the enthalpy is equal to internal energy plus the product of the pressure times the volume. That is this term, this is the final enthalpy, and this is the initial enthalpy. Then that means we have the heat at constant pressure is equal to the change in enthalpy is equal to the final enthalpy minus the initial enthalpy is equal to NCP dt. This is the final enthalpy minus initial enthalpy. That means here the heat is equal to the change in enthalpy. At constant pressure, the heat is equal to the change in the enthalpy is equal to the final enthalpy minus the initial enthalpy is equal to NCP dt Cp, because we are having constant pressure. That is how you can calculate the heat and the work done, and also the internal energy at the constant pressure when you have a system at constant pressure, or when you have the isobaric process. When you have isobaric process, the dP, or the change in pressure, is equal to 0. In this case, you have the internal energy, which is equal to NCV dt. Internal energy is always equal to NCV dt. The heat is equal to NCP dt. The heat, for the heat, we use Cp, NCP dt, because we are at constant pressure. Internal energy is equal to NCV dt. The heat is equal to NCP dt, is equal also to enthalpy, or is equal to the change in enthalpy. In this case, we have the change in the heat is equal to the change in enthalpy is equal to NCP dt, which is the heat, the total heat of the system. In this case, the work done is calculated by taking negative PV2 minus V1, or PV1 minus V2. So that is how we calculate the work done when you are having isobaric process, and the heat is equal to NCP dt. The heat is also equal to the change in enthalpy, or the final enthalpy minus the initial enthalpy. So now we have the internal energy is equal to NCV dt. We have the heat, which is equal to NCP dt, and we have the work done, which is equal to negative P dV.